Hello, everyone, and welcome to a new episode of MIT.nano Explorations. So today, it's a pleasure to introduce Daniel Rodan-Legrain. He's a graduate student in my group. He is working on the quantum electronic transport of graphene-based new Moiré heterostructures, and he will be telling us today about highly tunable junctions in magic angle twisted bilayer graphene tunneling devices. Please, if you would like to ask questions, wait until the end of the talk. The talk will be 30 minutes and then we will have 15 minutes for questions. You can ask the questions in person after the talk or through the chat. And Daniel, the floor is yours.
Thank you, Pablo, for the introduction. Good morning, everyone. My name is Daniel Rodan-Legrain, and I'm a grad student in Professor Herrera's group. And today, I'm going to tell you about a recent experiment on magic angle twisted bilayer graphene. So first of all, I would like to thank the organizing for putting together these great seminars and giving me the opportunity to present our research. So first of all, we have several platforms to study strongly correlated physics. One is by directly take a look at the quantum materials themselves, which we have studied for several decades. Another possible approach is to build cold atom analysis, which offer a higher control. And today I want to tell you about a recent platform for strongly correlated physics and superconductivity with a high tunability and accessible critical temperature. So for magic angle twisted bilayer graphene, the length scale of the superlattice is in between the one of the cold atom lattices and the one of the quantum materials. And the typical energy scale, which is on the order of 1 Kelvin, is also in between the two. And therefore, it offers a complementary approach. So this is the outline of my talk. I will first introduce graphene and magic angle graphene superlattices. Then I will present our observations on correlated insulator behavior at half filling of the superlattice density and on superconductivity. After that, I will basically show how we can exploit this unprecedented tunability within a single material platform to create fully tunable lateral Josephson junctions. Then I will present how in the same multi-gated devices we obtain spectroscopic evidence of the superconducting gap in magic angle twisted graphene. And finally, I will show how we can transform these devices into a single electron transistor displaying periodic Coulomb diamonds. So let me start from the beginning. The developments on 2D materials and van der Waals heterostructures have led to many analogies. One of the most popular ones is the one with Legos, since both of them can be stacked on top of each other in any possible way one can think of. However, with 2D materials, you can also do this. We can stack them one on top of each other at any desired angles, and the properties of the system dramatically change, as I will tell you today. And this is something you could not do before. You cannot do this when you grow ball crystals, and you cannot do this for a heterostructure, for example, grown by MBE. So in this case, a Moiré pattern forms, and the Moiré wavelength of the Moiré pattern, that is the distance between those soccer balls you see here in the screen, depends on the twist angle between the two sheets. And the Moiré wavelength increases very rapidly for small angles, thus giving us a unique knob to tune the band structure. So here we have the reciprocal lattices of graphene sheet 1 and graphene sheet 2. If we join the corners of these two hexagons, then we have the superlattice brilliant zone. Because we have a large Moiré wavelength in real space, then in reciprocal space, we have a smaller superlattice brilliant zone. So let me now show you a video of the electronic structure, energy as a function of momentum, as we rotate the angle from a relatively large angle, 3 degrees, towards smaller and smaller twist angles. So within this energy window, for 3 degrees, it basically just looks like graphene. So the first thing you will notice when I will run this video is that the superlattice brilliant zone becomes smaller and smaller here at the hexagon here. And then at around 1.8 degrees, so in a couple of seconds, you will have here this pair of bands that are separated from the highly expressive bands. And at around 1.1 degrees, so now, you get very flat bands. And then it continues evolving. So at 1.05 degrees, according to our latest calculations with a group of Caxiras, we get these flat bands separated by gaps to this other highly dispersive band. However, you know, the exact value continues evolving as more accurate calculations are performed. So flat in momentum space means, you know, by doing the Fourier transform, highly localized in real space. You know, localized where? Well, it turns out that the electronic states in the flat bands are strongly localized in the AA stack regions of the superlattice, where locally it seems like the 2 carbon atoms from the 2 carbon layers are one on top of the other. On the other hand, the density of states of the interconnecting AB and BA regions is low. So it is probably easier to see that in the top view, where the yellow spots are where the electrons like to stay, corresponding to this peak here. So let's talk about transport phenomenology. So this is the phase diagram of monolayer graphene, also large angle twisted by graphene, for example, 3 degrees. So if you take a look as a function of density and temperature, you only have one interesting point, which is the charge neutrality. And on both sides of it, here and here, you have metallic behavior. If we reduce the twist angle of the twisted by graphene, but not yet magic, and converting density to filling, we get this. I'm taking charge neutrality to be 0. We can add or remove 4 electrons to those bands here. So this pair of bands that are not yet flat. So by moving the Fermi energy, by either adding electrons or by removing them, we go from metallic behavior to band insulators. So positive fillings, meaning I'm adding electrons to the system, whereas negative fillings in that direction, I'm removing electrons or adding holes to the system. So let me stop for a minute and do a quick recap on single particle band theory. So I'm here plotting the density of states as a function of energy, assuming a system with only 2 bands. If the lower band is fully filled and the next higher upper band is totally empty, then this is an insulator. And basically this is called the band gap. On the other hand, if one of the bands is partially occupied, then the material can conduct electricity. This is a metal. And if we're dealing with single particle physics, then those are the only 2 options. However, sometimes it can happen that our Fermi level falls in the middle of the band, where in principle it should be a metal, but due to the strong interactions between the electrons, we can recreate a situation that is similar to this, where the system behaves like an insulator, and we call them correlated insulators, because the correlated between electrons opens a gap here. So now, if we are at the magic angle, this is the simplified schematics of the phase diagram. Details depend on various things and, slightly vary from one device to another. So with this notation, fields go from 0 at the charge neutrality to -4. So 4 holes per more unit cell, or +4 electrons per unit cell. So we have, again, of course, these band insulators, and at around 2 holes or 2 electrons per more unit cell, we have a correlated insulator. So across this talk, I will use D for Dirac, I for band insulator at filling -4, C for the correlated insulator at filling -2, and primes will denote positive doping, so on the electron side. Around the correlated insulators, both for the holes and for the electrons, we have these 2 superconducting domes, which I will label by S and S prime. And by now, several groups have observed a similar phase diagram for twisted bilayer graphene, which has actually been evolving very fast with input from several groups, and it's quickly getting enhanced in complexity. So let me show you some data at millikelvin temperature. And for that, let's measure the temperature of a large angle twisted bilayer graphene, larger than 50 degrees at least, whose band structure is similar to monolayer graphene as a function of density. So if our Fermi energy is deep inside our valence band, then we have an excess of holes, so the system will conduct well. If we increase the Fermi energy and eventually we reach the charge neutrality, then we don't have much carriers, and our large angle twisted bilayer graphene will conduct poorly. And if we keep adding electrons, then our Fermi energy is deep in the conduction band, and then our graphene will conduct well. So I'm now showing data for a device at a smaller angle, 1.8 degrees, but not yet magic. And near charge neutrality, you still have this characteristic V shape, like in graphene. But as you fill with electrons this band, or as we empty with electrons or fill with hole this other part of the band, at filling +4 and -4, we reach a gap here and here. Therefore, this is a signature of a correlated gap, and hence the labels C and C prime that I'm showing here. Okay, sorry, I messed up with the animation. So this is 1.8 degrees, but at the magic angle, this is basically what happens when you have a 1.08 degrees. So you have 2 correlated insulators that appear at half filling that I'm labeling by C and C prime. Sorry for that. So basically, we made new devices in a geometry that allow to measure superconductivity 2. That means shaped in a hole bar, basically look like this. And what we discover is that twisted bilayer graphene at the magic angle superconducts when we dope the system with holes. So we can measure the IV curves, which show finite current bias at 0 voltage drop. And because we can tune the density of electrons or holes by just changing the gate voltage here, similar to a parallel plate capacitor, we can also do this. We can zoom in around the correlator state for holes, so this state C, and measure what is the resistance of our device as a function of temperature and density. What you see is that this red region is the correlated insulator for holes. We can add more holes and we get a large superconducting dome. And if you remove a few holes or add some electrons, we get another superconducting dome here. And this diagram has some similarities with the phase diagram of cuprates, and this has generated a lot of interest. And we can do this for many more devices. These are data for devices ranging from 0.98 to 1.16. And what you see is that the shape varies from one device to another quite substantially. So one can obtain the RT curves at optimal doping for all of those devices over a range of different twist angles. And by now, we probably have, in total, a few tenths of magic angle devices. Here, let me show you a more cluttered graph that keeps constantly growing as we keep making more devices. So in fact, we started to map out what is the critical temperature as a function of twist angle at optimal doping. And we started getting some statistics. So what you see is that the superconductivity has the highest critical temperature on the order of 3 Kelvin, around 1.06 to 1.09 degrees, with the exception of a couple more disordered samples. And it seems to follow actually a dome shape. So if we move away from these values, we don't see any superconductivity. But this is not the end of the story. For the second part of my talk, I will focus on our most recent archive paper about highly tunable tunneling junctions. So the question that motivates this experiment is, why do we want highly tunable tunneling junctions? So this question is actually at the edge between physics and technology in the hope of making this topic appealing to our broad audience here today. So from a physics point of view, they offer a platform to study superconductivity and correlated states. And we actually have spent quite some effort in the group in that direction in the last year. They are also ideal, I would say, for studying physics and interfaces, for example, in Josephson junctions. And I would say they can even be used to shed some light on the intrinsic superconducting properties of the materials themselves. And I will show you all of that in the next few minutes. From a technological point of view, tunneling devices are actually ubiquitous in modern electronics. So in superconducting qubits, for example, state-of-the-art Josephson junctions utilize typically oxide tunneling barriers. But do suffer from disorder and are not electrostatically tunable. So if we want tunability, we basically need junctions with several different materials, and those may suffer from non-ideal interfaces and all kinds of fabrication challenges. So we actually demonstrated recently in the group, in collaboration with the group of Will Oliver, a graphene-based transport qubit that circumvents some of these issues. But now we have the ability to independently tune the electrons and the weak link into different phases in a superconducting junction made of a single clean material. And this enables basically an exponentially larger number of tunable configurations, which we can even use to make gate-defined circuits with magic angle twisted by graphene in future 2D integrated electronics, among many other possible configurations, such as highly sensible magnetic field sensor and other ones derived from single electron. The journal Science actually featured our work last week, claiming that these devices could power a new generation of superconducting electrons. I would say that's quite a claim. So let me first ask you a seemingly simple physics question. How do you know if your favorite superconductor is really a superconductor? Well, first, you need zero resistance. However, zero resistance can happen for many other reasons. So this is not an unambiguous test. A second confirming experiment can be the Meissner effect, the complete ejection of magnetic field lines from the interior of the superconductor when it's transitioning to the superconducting state. So I think it's fair to ask, is magic angle twisted by graphene truly a superconductor? Well, let's see. The first condition is simple. We have many devices now that show this type of curve. The Meissner effect, on the other hand, happens in all 3D superconductors. However, in 2D superconductors, we do not have proper Meissner effects for a reason that will become obvious, hopefully very soon. So an alternative unambiguous test to show superconductivity in 2D materials, in addition to zero resistance, is the Josephson effect. Brian Josephson predicted more than 50 years ago that when two superconductors are weakly coupled through what we call a weak link, which can be of many kinds and any dimension, basically Cooper pairs can tunnel through the tunneling barrier separating the two superconductors, and supercurrent can thus flow in the system. Josephson junctions are typically made from bulk 3D superconductors that are coupled via a weak link and have important applications in quantum mechanical circuits, for example, qubits, superconducting qubits, and even to define the standard of 1 volt, among many others. But in the 2D case, and in particular for magic angle twisted by graphene, where both the weak link and the superconducting electrodes are 2D, it is a little bit different than what you expect for bulk Josephson junctions. So 2D Josephson junctions superconductors screen external magnetic fields in a fundamentally different way from their bulk counterparts. While in bulk superconductors, the magnetic field decays exponentially at the edges within the London penetration depth, in the 2D case, it is basically essentially unaltered across the whole sample area. And this is because the screening currents cannot effectively expel the external magnetic field anymore. And this is why you cannot have Meissner effect in a 2D superconductor. So in this simulation, the color scale represents the normalized magnetic field inside the superconducting electrodes, and the streamlines represent the flow of the screening currents. So in a bulk superconductor, basically the magnetic field is expelled within region lambda of the junction, and it's actually locked inside the junction. On the other hand, for 2D Josephson junctions, the magnetic field distribution is not locked in the junction barrier anymore, and the Josephson electrodynamics is said to be non-local in this case. From the magnetic field distribution, we can obtain the distribution of the phase difference across the junction, which in turn gives the Fraunhofer interference pattern. So for a bulk Josephson junction, the periodicity is given by the classical Fraunhofer pattern, Fraunhofer formula, which is the flux quantum divided by the width of the device times the width of the junction. But it turns out that the Fraunhofer pattern of a planar Josephson junction differs noticeably from that of a bulk Josephson junction. So first, the high field periodicity is now given by 1.8 phi naught divided by the width of the device squared. So it depends solely on the geometry of the sample itself, and it's usually much smaller than the bulk periodicity. And second, the zeros of the critical current for the 2D planar junction are not equidistant at low fields, as in the bulk case. The truth is that already in the original paper, the Josephson effect was indeed present in magic angle twisted by graphene through disorder, that is, in an uncontrolled way. So this is the resistance as a function of perpendicular magnetic field and density. At the beginning, we thought that these dots here, that was not. Here, the resistance doesn't know what to do. Should I be superconducting or should I rather stay in the normal state? So it breaks up into islands, superconducting islands and insulating islands. So if we park and measure the critical current as a function of magnetic field, we have Fraunhofer-like oscillations, which tell you that you are actually looking at the Josephson effect between those islands. So now I want to show you how we can make Josephson junctions from magic angle twisted by graphene in a much more controlled way. So for that, we place a narrow top gate on our device. And this is the device structure. So the twisted bilayer graphene is encapsulated between hexagonal boron nitride on top and on the bottom. And we have a metallic gate that tunes the electron density through this bottom HBN sheet, and basically a narrow top gate controlling the electron state of the weak link. Bias voltage is basically applied between the drain and the source electrodes, and the forward probe resistance is obtained from these lateral contacts. The nanofabrication process is actually not trivial, and it involves a few key steps. First, we stack the different 2D materials and use the tier and stack technique to achieve a controllable twist angle between the two graphene sheets. If you're interested, we can discuss it later in the questions and answer session. And after that, most of the subsequent steps are performed in clean room and shared facilities and basically include a few e-beam lithographies, etchings, and evaporations. I actually take this opportunity to thank all the staff, and in particular, Mark Mondor for all his help. So if we only have one gate, this is the phase diagram. And the gated regions can be in any of these phases, including S, S prime, C, C prime, D, I prime, etc. So now, using the backgate and a narrow top gate together, we can define 3 separate regions within the same devices in series. So let me walk you through the complete dual gate parameter space available. I'm here plotting the resistance as a function of the backgate and the top gate. The transition between the different series combinations of the central and outside regions of the devices are seen from the horizontal and the diagonal lines of this map. So the diagonal features here in green, basically dependent on both VTG and VBG, are basically stemming from the dual gated region beneath the top gate, so this region here. And the horizontal features, which are independent of the top gate, are coming from the regions outside of the top gated area. So gated solely, by the back gate. So if we take a look at the intersection between a horizontal line and a diagonal line, for example, here, DC prime D, That occurs when the central region enters the C' correlated insulator state, and the outside regions are at the charge neutrality, and similarly for other intersections of the dashed lines. So if we take a line cut across this line, when there is no top gate applied, we simply recover the resistance as a function of the backgate phase, characteristic of magic angle twisted graphene. More interesting behavior happens around the dark superconducting regions with zero resistance. So in this case, supercurrent through a variable Josephson junction is observed across the device. If we use the backgate to globally tune the magic angle twisted by graphene into the superconducting state, for example, in this region here, and then we use the narrow top gate to form a weak link in the central region with another state, such as I prime, or C prime. So for example, SIS here indicates that the superconducting electrodes are in the, in the superconducting state, and the weak link is at the band insulating state. So let me actually set the backgate controlling the tunneling electron junctions into the superconducting state S, and sweep the top gate along this line here. So we can continuously vary the variance strength with the top gate voltage to achieve a weak link that can be switched from insulating metallic to superconducting regimes, generating a critical supercurrent, which is here represented in dark blue. Beyond the band insulator, we actually observed oscillations of the critical current with respect to the top gate here in a Fabry-Perot-like resonance occurring from the interfaces between the different phases, and are typically observed in high-quality devices close to the ballistic transport region. So let's now test the predictions we made for the interference pattern in 2D Josephson junctions. So based on the analytical expression 1.8 phi naught over W squared, we expect a periodicity on the order of 1.7 millitesla in our device when we put the Josephson junction in a magnetic field. So we first gate the device close to the superconductor band insulator superconducting regime. Sorry. Sorry for that. And we observed, I would say, a periodicity on the order of 1 to 1.5 millitesla for the finest oscillation, in agreement with our simulations and consistent with the so-called pair regime that governs the ultra-thin superconducting electrodes. If you take an approximation for the Bohr formula, here we have a periodicity, an expected periodicity of 8.5 Tesla. So this is far from our measured oscillation period. Similar values of the periodicity are also observed close to the SC'(S) and SI'(S) configurations. Alternatively, if we bring the weak link into the SS'(S) regimes, then the oscillations in the critical current disappear. So in this configuration, there's a rather complex density profile that actually transfers the whole phase diagram, but notably the junction kind of behaves like three superconductors. So let me now jump to the last point of my presentation, which is the evidence of superconducting gap and single electron transistors. So we made two more devices with a complementary geometry, and instead of a narrow top gate, now we have now we pattern two isolated top gates that are separated by a narrow gap, offering independent tunability of each half of the device. So in this geometry, we can basically reproduce all the main results I mentioned so far. But the fact that we can control the right and the left sides independently and in situ has dramatic consequences and enables the creation of versatile tunneling devices. So for example, we can do tunneling spectroscopy of the superconducting gap in magic angle twisted graphene. Tunneling spectroscopy measurements basically allow us to obtain information about the density of states in a sample. So this is the general schematics of the process. The normal probe is a metallic electrode, and then the tunneling barrier is some insulating state. The density of states of the sample, in this case magic angle twisted graphene, can be extracted by measuring at a few tenths of millikelvin the differential conductance, DIDV, between the probe and the sample. The bias voltage basically defines the energy at which the density of states is probed, and the Fermi energy can be tuned electrostatically with an electrostatic gate. So here, the tunneling barrier is actually provided by the bandgap present in the electronic structure of twisted graphene. So by setting the left side into the superconducting state and the right side into a metallic state in the next highly dispersive bands, we can actually perform tunneling spectroscopy from metallic magic angle twisted graphene into superconducting magic angle twisted graphene via insulating magic angle twisted graphene. So our electrostatic simulations show that the density evolves continuously and crosses the value n is equal to minus ns, at a position between the left and the right gated regions. And if we account for quantum capacitance effects in magic angle twisted by graphene, then we actually have this narrow region that is actually kept at density minus ns and acts as a tunneling barrier. So using this configuration, we obtain for the first time tunneling spectra of magic angle twisted by graphene in the superconducting state in two different devices. So the data basically show clear spectroscopic evidence of a superconducting gap where we have two very well-defined coherence peaks and a minimum at 0 bias. However, we do not, we do not obtain a hard gap due to thermal broadening, but we can obtain a quantitative measurement of the gap by fitting a model of the quasi-particle density of states, obtaining a gap on the order of a few tens of micro eV. As the temperature is increased above 300 millikelvin, both for devices B and C, the coherence peaks are actually significantly broadened due to thermal excitations. And as the temperature is further increased, the dip at 0 bias is suppressed and eventually disappears, basically indicating that the system is no longer superconducting altogether. Similarly, if we apply a perpendicular magnetic field larger than the critical fields at base temperature, then the coherence peaks also disappear and are suppressed because superconductivity is key. So these gate-defined tunneling junctions actually present a significant advance towards proving the superconducting order parameter in magic angle twisted by graphene. So last but not least, by further exploiting the flexibility of the split gate geometry, we can create a single electron transistor within the same multipurpose devices. So in an SET, electrons are actually spatially confined in a central region by tunneling barriers that weakly connected to the drain and the source So single electron transistors are particularly attractive nowadays for their potential to shrink circuits and also diminish their thirst for energy. So to achieve this, we basically tune the left and right sides into metallic states with densities beyond the full field density. And the central region, which is singly gated, is brought into a metallic state within the flat bands. And similarly to before, the calculated density of states, the calculated energy density distribution actually shows two insulating plateaux here and here with a density equals to minus ns, which results in an isolated island in the central region of the sample. At low enough temperatures, and provided that the tunneling resistance is large enough, electron tunneling is only allowed if there are available discrete energy states between the Fermi energies of the source and the drain electrons. Otherwise, the Coulomb blockade effects prohibits this type of tunneling. This is typically observed by measuring the differential conductance as a function of the source drain bias voltage and the gate voltage. So we basically observe well-developed Coulomb diamonds with a zero conductance in the blockade regime here in dark blue, thus obtaining a single electron transistor. So to sum up, I first introduced magic angle twisted by graphene as a system with flat bands in the electron structure. I hope I have convinced you that the twist angle degree of freedom is among the most unique characteristics of van der Waals structure. Then I presented some transport phenomenology focusing on correlated insulator behavior and superconductivity, and showed you why it offers a highly tunable platform for strongly correlated electron fields. In the second part of my talk, I basically exploited that our magic angle twisted by graphene can electrostatically and in situ exhibit a wide range of phases from metallic to insulator to superconducting phases to make versatile quantum devices. So I showed you magic angle twisted by graphene Josephson junctions, where we have the ability to independently tune the wiggling and the tunneling electrodes. And after that, I demonstrated edge tunneling spectroscopy in the superconducting state. Finally, by inducing a double barrier geometry, we operated the devices in a single electron transistor regime exhibiting Coulomb blockade. So from a more general perspective, where is this field of twisted 2D materials, twistronics? Where is this going? Is it just graphene and graphene, or is this more general? Well, turns out that any 2D material placed on top of itself and rotating, depending on the coupling, it is possible to realize a magic angle condition where you will have flat bands either everywhere in momentum space or locally in certain regions of momentum space. And by now, we have all the condensed matter behaviors in monolayer 2D materials. So we have metals or heavy metals like graphene. we have insulators, we have semiconductors, we have superconductors by themselves. And recently we also have magnets and quantum spin liquids. So by now, we can stack any 2D material on top of any other at any desired angle and introduce correlations if no correlations were present, like in the case of graphene, or modify existing correlations if they were not already, or modify existing correlations if they were not already there. So there is a zoo of possibilities, and many theory papers and some experimental papers are already exploring these directions. So probably the most important slide, I want to thank all my fantastic coworkers and collaborators without which none of this would have been possible. In particular, I want to thank my advisor, Pablo Herrero, Joan Cao, Jane Park, Sergio de la Barrera, Malika Randeira, and Oriol Rubies Riorda. Thank you everyone for your attention, and if you have more questions, I will be happy to answer them.
Very first question I have to get us going, it's remarkable what you can do with twistronics. It's remarkable what you can do with 2D materials. You have shown us an ability to use E-beam to pattern these 2D films, which of course raises a question on in the patterning process. What happens at the edges? What is the effect of the edge effects on these devices?
That is a great question. So usually we actually try to make sufficiently big devices that we can ideally, ignore the effect of edges, at least in this type of experiments. Other experiments actually study what happens at the edges. But there are actually lots of things happening at the edges. For example, through other collaborations, we believe that when you do some etching in our devices, actually the twist angle, so the twist angle is never homogeneous across the whole sample. We have two collaborations with the Weizmann Institute, with the group of Shah Halilani and with the group of Eli Zeldov, where we can map the twist angle across the device with a very high precision, up to 0.0001 degrees. And what we find is that the twist angle is not homogeneous across the device. Turns out that at the edges, when you try to pin the angle by etching, there are dramatic changes at the edges. So it's not that we can make devices that are completely homogeneous in twist angle, and it's not that we can ignore the edges. However, for this type of experiments, we try to study rather the bulk of the material by making these long whole bar devices.
That actually also brings a second question that I would follow. It's intriguing what you just said, which is that the actual twist angle, I'm assuming due to the folding of the sheet or maybe wobble in the sheet, is not maintained uniformly at 1.05 degrees throughout, for example, throughout your sheet. Consequently, I guess you are having multitudes of different electronic regions within that overlay sheets. I guess the precision of it is really just a question of what is the domain extent, so that would, I guess, limit your active area of a typical device, right?
That's right. So I actually like to compare magic angle twisted by graphene. I mean, I'm in the kitchen, so I like to compare magic angle twisted by graphene to this type of cellophane film. So imagine that when you put two twisted bilayer graphenes one on top of each other, you have two films that are one on top of each other. They are never going to be perfectly flat. They're going to have bubbles. They're going to have some ripples. So as you said, Vladimir, that's exactly the point. So the graphene will will have some angle inhomogeneity. So that's a new degree of freedom that we have in the device, angle inhomogeneity, which will affect the global transport of the device. And right now, this is something we cannot control. So we make a device, we aim at 1.1 degree. And when I say that a device has a 1.05 degree, what I actually mean is that the average when we do transport experiment is 1.05 degree between the electrodes which we're measuring. If we had a very long device and we would put many electrodes one after the other, we would see probably different angles. And even within these two electrodes, the angle might not be homogeneous, but what you're seeing is some sort of average between the twist angle. This is why when we give the twist angle, we usually give some error that tries to account for this twist angle inhomogeneity. So this is something actually we're trying to work on controlling, trying to make devices that are as long as possible with the minimum amount of bubbles. We're improving our techniques. We're being able to make larger and larger devices in this direction, but we're not quite there where we can make, actually we can make several micron devices that are very flat and have low twist angle inhomogeneity, but we're not quite there at the longer scale than that, I would say.
No, I think it also just emphasizes the need for the 2D material foundry that Pablo has been emphasizing for a number of years now. Pablo, I see you are able to reconnect, so please take.
Right. Somehow my Zoom crashed as Danny was going into the acknowledgement. Sorry, but I was able to reconnect. I guess Vladimir, you took over the chairship and even asked some questions. Are there any other questions by anyone for Danny? Maybe while people type, let me just add that indeed, Vladimir, I think while now the physics community is very happy to have a square micron of, magic angle twisted bilayer graphene and investigate all its properties, the field would advance enormously if we could create many devices, several microns each, or even, going into the hundreds of microns, where the twist angle would be uniform or varying very gradually, so that we could, let's say, in a 100 micron strip, make multiple devices with slightly different twist angles, and would allow us to investigate the whole thing. And for that, basically right now, we're limited by the mechanical stability, the thermal stability, the precision of our goniometers, and a number of things like that. So having next generation equipment to process state-of-the-art devices would be very valuable for the community, and to transition to possible applications, which, it's not crazy to think that some of these devices could lead to applications. So, but of course, for that, you need to be more able to more reliably produce them.
If I can add maybe some more questions until maybe a few more appear in the chat.
Please.
Which the 2D film on top of the other 2D film would have an optimal position, right? I mean, the optimal position would be 0 degrees, because that's how nature gives it to us. And that minimizes the energetic disorder between the top and the bottom, or maybe is a potential minimum. Consequence of that is to ask, as you twist it, some of the distortions you might be experiencing indeed could be due to the actual mechanical positioning apparatus you use. But I would also imagine there is some inherent stress and strain in this strained structure. You can almost think of it as a strained semiconductor, where you are forcing it in a position that is not necessarily the most optimal energetically for the system. That being said, there might be magic angles that are mechanically magical, meaning that more stable than others. Is that something that has been investigated at this point? Which is, is there a pushback by nature? You try this angle, but it's twisting you back into more optimal position, because it will minimize the energy of the vulnerable bonds.
That's an excellent question, Vladimir. So indeed, 0 degrees we know it's one of the stable minima of nature. So basically, if you twist the magic angle twisted by graphene, and for example, you heat it up, it will relax to a more stable configuration, very often towards 0 degrees. Same if we apply, for example, certain fabrication processes straight ahead, then, if they are violent enough, they will relax the twist angle. So we have developed some sort of techniques where the first thing we try to do is to pin the twist angle at 1.1 degree as soon as the stack is made. Usually by the exact same thing I was telling you before. We know that the edges pin the angle, even though it changes the twist angle. So we believe that by doing an etching first, we're going to be able to pin the twist angle, and therefore avoid it to be relaxed towards 0 degrees. Right now, the only magic angle twisted by graphene that has been experimentally demonstrated in graphene is 1.1 degree. There are other magic angles that are predicted, 0.55, and then it scales down, but none of them has been demonstrated experimentally. In particular, also because of this twist angle inhomogeneity. If you're far away from this twist angle, they are probably not as robust as the first magic angle, 1.1 degree. So there are other TMD systems, for example, that have a larger window of potential magic angles that would lead to a flat band structure, but then we're going to other different materials.
Given the time, allow me to just ask one last question, and I'm going to pass it to Pablo to close the event. I I have been fascinated from the very first demonstration that your group has done this by the periodicity induced through the twist, where on the nanoscale, you're able to make conductive, not conductive, indeed, through that repetition, Josephson junction, superconducting demonstrations, all of those indeed have been demonstrated. It also leads you to recognize that this particular phenomena might make us understand conduction and superconductivity in ways we couldn't do before, because finally we have a system that's repetitive on that scale in this domain region control that we could never do quite before in such precision. As you look forward, your demonstration of superconductivity is still requires sub 1 Kelvin type of cooling of the systems. Do we see an ability to maybe in a superconductive regime or in other regimes achieve behaviors of matter at more accessible temperatures, hence yielding the possibility of beyond just physical appreciation of why the world works the way it does, yielding maybe technological advancement akin to the way you're starting to explore with Will Oliver's group?
That's another great question. So indeed, this is one of the questions we had from the very beginning. If we want to make it accessible to the public, we need to be able to either increase the critical temperature at which all of these phenomena happen, or change dramatically the technology nowadays, which seems much harder to do. So I will quote one of Pablo's examples he gives in his talks to respond to this question. And there's actually some theoretical prediction from a group in Norway, I forgot the name, where they claim that if you have graphite that is misaligned one with respect to each other, as you increase the number of layers, potentially then the critical temperature presumably increases. So now we can try 3 layer, 4 layer, 5 layer. And if we go to bulk graphite, where the layers are twisted one with respect to each other, potentially we can increase the critical temperature of magic unconductive graphene. For that, I would say we also have to kind of reinvent a little bit the techniques we're fabricating these devices. So right now we take a long graphene, we tear it apart because it's one single piece. We know the crystallographic axes are aligned, and we tear apart half of the graphene with an HBN flake. We put it on top of each other. We rotate 1.1 degree with a motor, and we stack them on top of each other. So that you can do maybe 1 time, 2 times if you really push it and have a long graphite. It is not very scalable if you use micromechanical exfoliated graphene. We could go to CVD graphene. We could use to any other type of long scale made graphene, and eventually try this type of experiments in a much bigger scale. So there is a possibility that this will happen. I guess it's just a matter of keeping trying, and more PhD thesis coming.
That's great to hear. Although leave it to Pablo to conclude. Thank you.
Okay, thank you very much, all of you, for attending this MIT Nano Explorations talk. Thank you very much to Danny for the talk. And just to conclude that I think this field is really emerging and opening a big avenue for exploration, as the title of this seminar series is. And I hope that there will be plenty other physics talks to follow up in this series. Again, thank you very much, everyone, and we'll be looking forward to the next MIT Nano Explorations talk.
Thank you, everyone.